Blue Tech Around the World, the reference podcast for blue technologies and ocean innovation.
On Wednesday, February 12th, the KEMVNet collaboration published a historic detection in Nature, the observation of an ultra-high energy neutrino, the most energetic neutrino ever observed. We have already seen on this channel that space technologies could help monitoring the oceans. This time it's the opposite. The ocean is used for space exploration and particle detection. With this incredible news, I'm taking the opportunity to launch a brand new format on the channel, Blue Capsule. These are short videos that react to scientific news or explain an innovative technologies related to the sea and the ocean. And what better way to kick off this series than with a collaboration with Grégoire from Livre Science, who helped me write this episode. So today we are diving into a fascinating topic: how the ocean helps us unlock the mystery of the universe. Neutrino is a particle that interacts very little with matter, so it's very hard to detect. They are almost massless, and they fly through the universe at very high speed. Right now, billions of neutrinos are passing through the Earth with no interaction whatsoever, are truly ghost-like particles. However, there is still a small probability of collision, and sometimes a neutrino will strike an oxygen nucleus under the ocean. This interaction produces a highly energetic and therefore very fast muon. A muon is another particle similar to an electron, but much more massive. The speed of the muon is, of course, lower than the speed of light in vacuum, which is 300,000 km per second, but in water, the speed of light is lower. It's not 300,000 km per second, but only 225,000 km per second. So the muon can easily move faster than light in water, and this will create an electromagnetic shock wave. Already know this phenomenon in the air with sound waves, when an aircraft breaks the sound barrier by exceeding the speed of sound, 1,200 km per hour, create a sonic boom. Similarly, when a muon moves faster than the speed of light in water, it generates an electromagnetic shock waves known as the Cherenkov effect. So we need water to make this observation. Couldn't do it at the surface or in space. And for this specific experiment, the best sensors is the ocean itself. To detect the shockwave of light, the KEMVNet collaboration has placed sensors at great depth, 3,000 meters under the sea. You might wonder, why go so deep? The answer is that we are not actually interested in muons, but in neutrinos. The problem at the surface is that billions of muons are constantly raining down due to cosmic rays. However, the only particle capable of reaching 3,000 meters of depth is a neutrino. So if we detect a muon at this depth, it must have been produced by a neutrino. This allows us to detect neutrinos indirectly. The KEMVNet collaboration is part of the European Strategy Forum on Research Infrastructures and operates through detector. The ORCA detectors, located on the coast of Toulon in France, is installed at depth of 2,400 meters and detects neutrinos in the giga-electronvolt range. 1 electron volt is the typical energy of an electron in an atom. 1 giga-electronvolt is a billion electron volts, which is already a very high energy for particle. The collaboration has also installed a second detector, ARCA, off the coast of Sicily at a greater depth of 3,400 meters. The detectors here are spaced farther apart than in ORCA. 700 meters line high have been installed 90 meters apart. ARCA functions like a telescope of a 1 cubic kilometer volume. ARCA is less precise than ORCA for measuring neutrino properties, such as their mass, but it can detect higher energy neutrinos. As mentioned, 1 giga electronvolts equals 1 billion electronvolts. 1 tera electronvolts equals 1 trillion electronvolts. And 1 peta electronvolt represents 1 quadrillion, 1 million billion electronvolts. And 2 years ago, ARCA detected neutrino with 220 peta electronvolt, 220 million billion electronvolts. For the past 2 years, scientists have been working hard to confirm and refine this discovery. And since Wednesday, it's official, this is by far the most energetic neutrino ever detected. So here's how it works. ARCA consists of 230 vertical detection lines, each containing 18 spherical sensors modules, and each sensor is equipped with 31 photomultiplier tubes. The sensor modules must withstand pressure of over 340 times the atmospheric pressure. Here is the interior of a module. You can see the photomultiplier tubes and the calibration instrumentation. All of this creates a complete 3D network to capture the Cherenkov light we discussed before. But there is still a problem to solve. The detection units tend to tilt with the circumference, so we have to track the position of the sensor modules with acoustic emitters and their orientation with compass. The goal of the ARCA telescope is to get an angular resolution of 0.05 degrees. This is necessary because we want to know exactly where the source of the detected neutrinos is located in the sky. To achieve such a precise angle, we have to know the position with an accuracy of 20 centimeters and orientation with an accuracy of 3 degrees. Given the speed of the particles, 20 centimeters correspond to a delay of 1 nanosecond, so it's quite precise. The first method with accelerometers tracks the relative position and orientation of the optical modules. And the second method tracks the absolute orientation of the complete network. We know that cosmic rays are blocked by the moon and the sun, so there are 2 blind spots in the sky for the detection of muons. To get the absolute orientation, we just need to align these 2 spots in the detector with the actual direction of the moon and the sun. So here's what happened. A neutrino from space collided with a water molecule. The neutrino then disappeared, giving birth to a high-speed muon. Then, as the muon traveled through the water, it created a shockwave of light, a well-known Cherenkov effect, which was detected by the entire network of optical sensors. By the way, here is what the sensors look like from the outside. They are quite large, and by analyzing the detection data and performing extensive calculation, researchers were able to estimate the initial energy of the neutrino and also its detection. We know of various objects and phenomena that can emit neutrinos: the sun, supernova, exploding stars at the end of their lives, and neutron-star mergers. But when scientists reconstructed the trajectory of the particle, they quickly realized that it didn't come from our galaxy. It must have been created by a very energetic process located at a great distance. This image represents a sky map in the detected direction. The red star at the center marks the origin of the neutrino, and within a few degrees around it, we can see known energetic sources. Purple circles represent gamma ray sources, such as gamma ray bursts. The blue squares represent X-ray sources, and the small orange cross marks a bladder, a compact galactic nucleus bombarding us with radio waves. Despite intense research, astronomers found no supernova, neutron star mergers, or gamma ray bursts in any known galaxy in that direction. So a new hypothesis has emerged. This could be the first detected cosmogenic neutrino. Cosmogenic means it was generated in cosmos, far from typical sources like supernova. The entire universe is immersed in low-frequency radiation, the cosmic microwave background, leftover light from the Big Bang, which has lost energy over billions of years. It is possible that an ultra-fast cosmic ray, such as a high-energy proton, interacted with this cosmic background, creating our ultra-energetic neutrino. This marks the beginning of a new era in astronomy because neutrinos are the perfect cosmic messengers. They barely interact with matter, allowing them to travel vast distance with no perturbation. And since they have no electric charge, they are not deflected by cosmic magnetic fields, meaning the direction of their detection points exactly to the objects that produce them. So the more neutrinos we detect, the more we will learn about our universe.